I did put it on live.
Okay, yeah, then let's start. Michael, please.
Yes, very warm welcome and good afternoon to everyone who made their time to come to this, say, public gathering in a way, even though it is online. Let me just very briefly say my name is Michael Bakkes. I'm an associate professor at the University of Namibia, and I will guide us through today's webinar. And without any further ado, I want to call on the stage, so to say, Professor Thebe Medupe, who is the president of the African Astronomical Society.
Thank you very, very much, Michael. Welcome, colleagues. As you heard, my name is Professor Thebe Medupe. I'm the president of AfAS, and I just the reason why I'm here is to extend our congratulations to the involvement of our scientists, African scientists, in this amazing collaboration called the EHT. And basically, the purpose of this collaboration is to improve the capability of the very long baseline interferometry, the VLBI. And this collaboration, the aim is to produce science at a very high level, with the promise to produce cutting-edge scientific discoveries, such as the ones that will be presented here this afternoon. And also, I need to remind colleagues that one of the main goals of AfAS is to foster collaboration amongst African astronomers, but also between African astronomers and astronomers across the globe. Therefore, the activities of EHT are of direct interest to us. It is with great pride to learn that Africa has participated in the research that has produced the latest mind-blowing results of revealing an image of the supermassive black hole at the center of our galaxy. On behalf of AfAS, I'd like to congratulate again Prof. Roger Dean and his team in South Africa. We encourage him and other scientists to get involved in similar kind of high-level scientific collaboration, and also to continue representing Africa in such international research collaborations. With those words, thank you, colleagues, and enjoy the presentation this afternoon.
Thank you so much, Professor Thebe Medupe from Northwest University. Then I have the pleasure to invite to the stage Takalani Numangani, who is the director at the Department for Science and Innovation, and has walked a long way together with us astronomers on realizing all these astronomical dreams we have here in Africa. Takalani, may I ask you to please come up? Sorry, Takalani, are you with us? We can't hear you yet. So I'm not sure. It seems there might be some technical glitch. So let's wait maybe two more moments. Mr. Nmangani.
Charles needs to make
Nirush?
Takalani co-host because we disabled unmute for everybody else, and then that doesn't seem to work.
Hello, can you hear me?
Yes, we can hear you now. Thank you.
Oh, okay. It looks like I can't open my video at the moment. It's not allowing me to
put my video on, but as long as you can, oh, okay, there I am. Okay, good afternoon, everyone. Thank you, Program Director, and from the Department of Science and Innovation. I'm very pleased that we are co-hosting this webinar together with the African Astronomical Society. I think it was, we had, similar thinking that, we should have this session to showcase, what is happening and our, African involvement in this work of the black hole. Of course, black holes in astrophysics and physics generally are a very sexy topic, because black holes obviously command a lot of influence, in the dynamics of the universe. From our side, we pleased that our various funding instruments from the DSI and the NRF are allowing our astronomers to participate in various observations and experiments in this era of multi-wavelength astronomy, multi-messenger astronomy, where it presents a lot of opportunities, even for our upcoming generation of young scientists to participate in various opportunities. So we're very thrilled about that, and we continue to support the development of African astronomy to make sure that we become, a very significant in this sector in terms of the scientific involvement and in other ways. As you all know, that Africa continues to host a number of different telescopes of them, for example, the SKA, the Mercad, SALT, and also the AMT that is coming to Namibia, and many other instruments across Africa, which really shows that Africa is indeed, becoming, and slowly but for sure, a significant player in astronomy. So I would like to wish you good luck for this meeting, and let's all listen and enjoy the webinar. Thank you very much.
Yes, thank you so much, Takalani Numangani from the Department for Science and Innovation. And let me take this very opportunity to thank both our hosts, the Department for Science and Innovation in South Africa and the African Astronomical Society, for making this webinar possible. With that, we come to the program point where I have the pleasure to introduce very briefly what this whole webinar shall be about and whom we will have the pleasure to listen to. We will now start with, well, the webinar talking about, as we heard, the results that were presented by the Event Horizon Telescope collaboration. And I'm pretty sure you have all seen the invitation leaflet, which shows the newly released image of the black hole in the center of our own galaxy, which was indeed a major achievement. And we will hear about different aspects of South African or African involvement in that. And for that, we will start with a couple of presentations, and we'll have Professor Roger Dean to go first. He's a professor at the University of Witwatersrand and an extraordinary professor at the University of Pretoria. Just very briefly on his CV, he completed his doctorate in 2012 at the University of Oxford, then went to the Rhodes University and the University of Cape Town, so coming back home, to South Africa, and then moved to the University of Pretoria on a faculty position, and meanwhile is mostly at the University of Witwatersrand, where he holds the DSI NRF SKA Chair in Radio Astronomy, and is also director of the WITS Center for Astrophysics. His research interests are quite broad, and I don't want to name them all here, but well, quite importantly for today, he's quite interested in distant galaxies to the inner accretion disk of those supermassive black holes, and he makes use of data from the Mercad radio telescope, which is indeed in South Africa, and makes use of very line baseline interferometry, particularly in the Event Horizon Telescope network. And we'll hear from him about that. Then we will have Inian Natayanan, also from the University of the Witwatersrand, who is a postdoctoral fellow there at the Center for Astrophysics, and he was previously a postdoc at Rhodes University. He gained his PhD in astronomy from the University of Cape Town and was always working on algorithms and applying statistical methods to problems in radio astronomy. He joined the EHT collaboration in 2018 and also there works on algorithm development and data analysis for the Event Horizon Telescope. Then we will have Professor Drew Brink, who is an associate professor in the Department of Mathematics and Applied Mathematics at the University of the Free State and also an associate of the National Institute of Theoretical and Computational Sciences. Being from Bloemfontein initially, she obtained her PhD at Cornell University and later won a Price postdoctoral fellowship at Caltech, where she worked under or in the group of the Nobel laureate Kip Thorne. She worked mostly, or works still mostly, on testing general relativity, and in the context of that, she tries to use black holes, pulsars, and gravitational waves. She has been, before taking up her current position at the University of the Free State, with the, I think it was called National Institute for Theoretical Physics, which is now called the National Institute for Theoretical and Computational Sciences. I will have the pleasure as well to give a very brief update about the African Millimeter Telescope that was briefly mentioned, and then we will have a Q&A session. And without any further ado from my side, I want to ask Professor Roger Dean to start telling us about the EHT, the science overview, the next generation EHT, and VLBI in Africa. Oh, I already see the slides popping up, so Roger, please go ahead.
Thanks very much, Michael, and good afternoon, everyone. Thanks for the kind introduction, and thank you very much to AfAS and the DSI for hosting this. While there were some offensive messages posted by a Zoom bomber under my name just before this, maybe that's a tip of the hat to the popularity of the events that AfAS and DSI put on, that you actually do have a Zoom bomber that pays attention and comes in. But thanks very much for hosting this. I think it's timely for a number of reasons, and very much aligned with, as the president of AfAS mentioned, fostering collaboration between African nations and indeed with Africa and the world in astronomy. And I think the EHT and millimeter astronomy and VLBI in particular are extremely well aligned and well placed for this. So delighted to participate in this, and thank you very much for the invitation and for arranging it. So we're going to have two presentations from the two of us that were part of the Event Horizon Telescope. I'm going to tell you a little bit about the array, the science, etc., and then Inian will dive into the actual result, the physical meaning. But the theme here is broader than just the EHT and the Sagittarius A results. Really want to be talking about VLBI in Africa, and what I would like to put forward and come back to, and perhaps in the Q&A, is using these wonderful results as an exemplar of what VLBI can do, and the wonderful future that's ahead in VLBI, and perhaps using that as a catalyst to really kickstart VLBI that we want to connect Africa. All right, so my talk will just give you a brief overview of the Event Horizon Telescope Array, the science overview in addition to the primary science, and then the exciting sort of decade that we have ahead, looking towards what we can loosely call as the next generation EHT. And then all these themes, as you will see, science, technical, and human expertise and collaboration on the African continent are very much a part of the push to enable very long baseline interferometry across the continent. So I'll be talking about that. So the EHT is not just a global spanning array, it's a globe spanning collaboration of over 300 scientists on 5 continents. And this is us back in 2018. You can see Indian here in the front row, and I'm hidden back there, but you'll recognize some of the famous astronomers part of this. They're located in these sites. So you can see Africa is represented, but as we'll come back to, we want to enhance that and have many more countries on the continent involved. And the 13 primary institutes that make up the EHT board are, some of the major universities on the planet, MIT, your MITs and Harvards and others, Max Planck Institute for Radio Astronomy. And these are the ones that put the big investments in that fund the telescopes that make up the EHT array. But there are affiliated institutes, and you can see South African institutes there, the University of Witwatersrand, Pretoria and Rhodes University involved. And then, as was mentioned, not only is there investment from the NRF DSI into the AMT, but there's been direct investment in the EHT collaboration already. My DSI NRF chair in radio astronomy at WITS, and Indian is his postdoctoral fellowship is funded by that chair as well. All right, so let me get into the instrument. So what you have is a globe spanning array, a whole lot of nodes in this network. And you can see 3 examples on the right-hand side, some fairly extreme sites. On the top, Hawaii, the SM, in the middle, Alma and Chile. And at the bottom, you can see the South Pole with a casual military aircraft with skis just landing alongside. It needs to be in these extreme sites because when you observe at the wavelength of light that the EHT does, which is 1 millimeter, affected by the water vapor in the atmosphere. So you need to go quite high to get as high above that as possible. Whereas if you look at, so the EHT sits around here, around 1 millimeter, whereas the SKA is more sort of lower frequency, so it doesn't have to go to such high sites, and it doesn't need to use dishes that have the surface accuracy and precision that this has. What does the EHT observe? Well, our primary target is supermassive black holes, and what we're doing here is zooming into what's known as the accretion flow. This is swirling hot gas in red there, swirling into the supermassive black hole, and sometimes you have a twisting of magnetic fields there, and the idea is that you have these gray jets that are emitted as well. What we're trying to do is get right into the center there with the Event Horizon Telescope. You can see that sort of dark spot, and here's a still frame of that, which is expanded. There's the accretion flow in red. We have these red jets that we think are linked to the spin of the supermassive black hole and twisting of magnetic fields in that vicinity, which acts like a giant natural particle accelerator, like the Large Hadron Collider, accelerating particles out close to the speed of light. But if you zoom in and you use the Event Horizon Telescope, this is the image that we released from M87 back in 2019, and a simulation of what that is. Known as a photon ring, and the event horizon is further in. The photon ring, as I'll show in a moment, is gravitationally lensed. Now, there are 2 key concepts that you need to get to understand what this black hole shadow thing is that we're trying to image with the Event Horizon Telescope. The first is light bending around black holes because they're so massive and they actually curve the local space-time. But some of the light is actually crosses what's known as the event horizon, and it is captured by the black hole. So this simulation gives you a sense of that. You've got photons of light traveling through the universe. Some of them are coming quite close to the black hole. Their paths are bent by it. Some are so close that they're actually orbiting the black hole for a short period of time. And what happens there is you have this preferential ring of light around the black hole and a deficit of light towards the center. This is effectively what's known as the shadow. That's the simulation of it, and that was the EHT image of M87. Now, as you've already seen with some of those movies, the key thing there is this is dynamic. So here you're seeing different movie frames of that accretion flow falling into the black hole. The light is bent around the black hole, and you see this enhancement around and sit in the middle. But also, if you change the inclination, as is happening on the right-hand side here, you always see a shadow-like feature because light is always being bent around the black hole. There's always a deficit towards the center because of that photon capture. And so we have to deal with many frames. A good example of this is a recent master's student graduated of mine, Michaela Menegaldo, who took 100,000 of these kind of movie frames and organized them using an unsupervised learning technique. But this just illustrates, you can see different sizes here, you can see different paths, and these are different inclinations and other parameters as well, like the electron ion temperature and the accretion disk. Now, in a nutshell, we're using this rotating globe with nodes of the network spread across the globe to collect mutual observations. They have to be staring at the target at the exact time and be measuring these, and very high time precision of the sensing the voltage change from the black hole. And we're trying to image this thing, which is of order the size of a donut on the moon, as I think analogy that many people have seen in the popular press. Now, the main topic of today's webinar in terms of it is the black hole in the center of our Milky Way. And I'm just going to show you this video that you might not have seen as part of the release a couple of weeks ago. We're zooming through, this is, beautiful deep universe, many galaxies. We zoom into our galaxy, which is a disk-like galaxy or spiral galaxy. We sit about 2/3 way out of that. Sitting in that disk is the Earth. And these antennas are spread all across the Earth in some, as I've shown, fairly extreme sites. We're going to now zoom into one of those extreme sites, a volcano, 5,000 meters in Hawaii. You can actually see there are two imaging stations there, JCMT and SMA. I'll come back to that a little bit later. But these are the SMA dishes staring towards the center of our galaxy, peering through a whole lot of ionized gas towards that beautiful Mercad image that was released earlier this year by Ian Hayward and collaborators. Further in still is what was awarded the Nobel Prize in 2020, these orbiting stars around an unseen mass. And what we released 2 weeks ago was this ring of plasma right at the center, about 100 times closer than that, which is the final orbit of plasma just before it falls into that event horizon. So Inian's going to be telling you more about that. We had our own private, separate press event, smaller press event here in the Wits Planetarium just 2 weeks ago announcing this. It really is quite remarkable now. So in the last 3 years, the EHT has released these 3 images, 2 of them, one in polarized light and one in total intensity, and now a very similar sized ring, a bit uglier and scruffier. As Stephen Colbert said, okay, let's do a funny one. But what's remarkable is this is approximately the same size, but it is about 1,000 times different in mass, the black hole at the center of our own galaxy. You can see here M87 shadow would encapsulate our entire solar system, whereas a far cuter black hole shadow, which is Sagittarius A star, would fit within inside the Mercury's orbit, our sun. So what's really interesting about that and really important is that we're testing general relativity over 3 orders of magnitude in mass. It really is a remarkable feat, and it's holding up. It's fitting this predicted shadow diameter very within our measurement uncertainties. But more on that in Inian's talk. So science is these tests of gravity, but not just that. There's a lot more science to the EHT, especially as it begins to expand. It's understanding jet launch, and there've been a couple of papers on that already. You might have seen this in Taurus A papers. There's what will be a completely unprecedented view of binary supermassive black holes because of this incredible angular resolution or sharpness of the image that we have. The same data are being used to search for pulsars, spinning neutron stars that act as the most accurate clocks in the universe in the vicinity of the Galactic Centre. They'll be with the expanded array and the new science case that within the next generation EHT is just a remarkable probe of transient sources. And there's just, there's a suite of this high energy, multi-messenger, multi-wavelength astrophysics that can be done with the EHT. Now, if you look at that overlaps completely with square kilometer array science. Sure, there's other square kilometer array science as well, which many of us on this call are involved in. But you can see that the EHT is not just this black hole shadow imaging experiment, but there's a whole suite of science to be done. And let me give you an example of that. I think many of you might remember this wonderful Mercad inauguration image, which was later became observed over a slightly larger area, that scale there, and led by Ian Hayward, a Nature paper back in 2019. And what he found was basically him and his team, what looks like a bubble-like outflow structure centered on the supermassive black hole that's right in the center there. So you can see that these are completely different scales, but it's so important in astronomy, if we really want to understand these things, is to be able to capture all those scales. So the model put forward in this paper was actually that it was a star formation event that is likely driving this outflow. But zooming in and actually imaging the activity around the supermassive black hole right now is a critical ingredient in understanding things in this galaxy and in others. There's also a big multi-wavelength campaign. This is just to give you a sense of that. So Sagittarius A star, here's some of the coverage of a number of facilities, including HESS, and Michael might tell you a little bit about that in a bit. And then here's a paper that we released last year, M87 coverage across the electromagnetic spectrum. So, there's a lot of synergy here with multi-wavelength facilities. What's really exciting now is looking towards the future, the next generation EHT. You can see in yellow were the 2017 stations. Since then, there have been 3 stations in orange, Noema, GLT, and Kitt Peak. And then prospective sites for the next generation EHT are in cyan, and you can see obviously Hamsburg sitting here. What that buys you is incredibly enhanced imaging capability. So you can look here that it's not just about a shadow, but these shadows, at least in the M87 case, are, the anchors from these large-scale jets, these relativistic jets that we see. And we want to image both the shadow with higher precision. This is the next generation EHT simulation. You can see that it's far finer details, so the general relativistic tests can be done with far higher precision, but also the ability to have more stations and more shorter baselines, and I'll return to that later, in being able to see the connection between this and the larger scale jets. We want to understand the genesis of these jets and follow them to larger scales, which is critically important for a whole range of science cases, not EHT, but also SK. So as you'll hear many times, I think today, Africa has a remarkable geographic advantage in participating in these kinds of experiments, the EHT, the global millimeter VLBI array as well. But we don't have any stations here yet. To give you a sense of that, and one of the key enablers that will provide is actually making movies of what's going on. So this is an update of Ian Hayward's remarkable portrait of our Galactic Centre with Meerkat. But right in the center there, this is courtesy of Michael Johnson at Harvard, simulating if you had 3 African stations, so one at Hamsburg, one that was put in the Drakensberg as a kind of representative, and then Kilimanjaro. You really start, we are not sensitivity limited, we are limited by the number of nodes. So even less sensitive nodes that are in the right places, like AfAS, can remarkably enhance the imaging quality and the ability to make movies. And movies equal far more robust tests of general relativity. I just want to point you to the timer here. This is hours, minutes, seconds. The plasma around Sagittarius A star, and remember, we're viewing the Earth as viewed from the center of our galaxy, is able to image this plasma, which is orbiting around the black hole on timescale of minutes. And because it's changing on timescales of minutes, it's like taking a long exposure photograph of something that's moving very rapidly. And, we'll talk about this more, but it really the game-changing enhancement that sites on the African continent can make. And Michael will give you a status update in a moment, but just to kind of show you this, one such site, potentially up here on the Hamsburg at 2,340 meters, or down at the HESS site. The CES telescope will move there from Chile and be refurbished. This was an absolute delight to actually visit here. This is me standing on that edge after the scariest 4x4 ride of my life, but it just an absolutely gorgeous site up there. We got to go here as part of a South Africa-Mexico delegation funded by DSI and NRM. Tina Stander from UP wanted to arrange a Meerkat visit for our Mexican colleagues, and I said, no, let's go to the AMT. Let's because obviously our Mexican colleagues host one of the major EHT stations. So this project is, as Michael will tell you, led by Radboud and University of Namibia. We're really holding thumbs that they will be securing funds to fully fund the project in the coming months. So several Dutch and European grants that are being assessed as we speak. But there's already been a whole lot of African involvement in this. Beyond just Namibia, which I think is kind of giving you the sense of how Africa is growing in its prowess as an astronomical host nation, but also the expertise, and perhaps even more importantly, the expertise that are now found on the continent. So, you know, there's UP Hartwell radiometer work that there's a radiometer on its way up to the mountain right now, well, to the his site at least. I'm part of the AMT Science Council. Andre Young, a former Soreo-funded PhD student, is the AMT project engineer at Radboud University. There's Soreo-funded UNAM, UP AMT students and more to come. And the simulation software that's been used to kind of predict the enhancement of the EHT with the AMT. This is South African developed. So really, you know, there's lots of synergy here, lots of collaboration already, and we're looking forward to even more. What I'd like to talk about, just closing out, is just, you know, the idea of a much more lower cost, small diameter South African EHT station that will add a whole lot of value to the AMT's contribution to the EHT. As I said, we're not sensitivity limited. We're limited by the number of nodes we have around the world. And another station will leverage off the extra sensitivity, the higher sensitivity of the larger AMT network, but also critically enhance the calibration of African baselines. As I mentioned earlier, SMA and JCMT are co-located on the Hawaiian volcano. ALMA and APEX are co-located on the Chilean altiplanos. That is a remarkable enhancement to the amplitude calibration, which in turn, to those that are more aware of radio interferometry in the audience, gives you a imaging dynamic range enhancement. So you're able to image more things, and you're actually, more stations equals more, a stronger ability to actually, a better ability to actually make movies of Sagittarius A style. And then key, as I mentioned earlier, we want to not just image shadows, but see this link with the larger, these base pairs of antennas around 1,000 kilometers, which are very scarce in the EHT, are critically important to image large scale structures. So an AMT and South African pair would make a remarkable contribution there. I think, you know, if you're thinking about a far smaller scale, South African EHT station, this really is enabled by, you know, established sites with, you know, support staff. We can leverage off our world-class telescope engineering that's, you know, on step towards the SKA and Mercad, and then a whole lot of interferometry expertise. I mean, that's why Inian and I were invited to be EHT. It's direct benefits from the Mercad and SKA and African VLBI investments that have been made. And then I would say, you know, a strong holistic alignment with what you can call SKA 1.1 and potentially co-location, but we can discuss that more in the Q&A. But I think a game changer here is having intra-African baselines to develop African expertise, not just hosting at one site, but hosting at multiple sites to be able to do some of this together on the African continent and build up our expertise and maximize our geographic advantage. For the engineers perhaps in the room that are interested, the game-changing technology, we're talking about lower sites here. And the reason we talk about that is because of our Korean colleagues who've pioneered this new technique of observing multiple frequencies at the same time. And what that means is, think of it as adaptive optics for a millimeter single dish. And what that adaptive optics at millimeter frequency wavelengths allows you is basically to go to lower sites, which means you can go, you spend far less on infrastructure and operating costs, which I think, you know, when you combine that with our African geographic advantage, the future is very bright for African participation in the EHT. And Inian to paint this this picture and the expertise development toward that in this Conversation Africa article recently. I just want to close with, you know, obviously there is this natural synergy with the square kilometer array and the African component of that. But if we look at the future of the next 10 years, VLBI is going to become a critical component, not just at centimeter wavelengths of the SKA mid, but meter wavelengths with SKA low. And you can see here, this was a meeting I was on the SOC for earlier this year. This is SKA VLBI at centimeter frequencies in yellow here, And then there are ambitions to do the same thing at millimeter frequencies centered on SKA low in the Western Australian site. But at the same time, what was the original vision of the SKA was to have a high frequency component. And that was very highly ranked in the US review and is very likely to be funded. And this will be operating from 1 to 100 gigahertz across the US, down to Mexico, and further abroad as well. So if we want to participate in this, really building the expertise is key. And I want to highlight the wisdom here from previous major projects. Our Vice Chancellor at WITS, Professor Zeblon Vilakazi, gave a lecture to the School of Physics on Friday, and he reflected on the incredibly important role of even a modest cyclotron at Itemba, playing such a critical role building up expertise towards South Africa participating in the Large Hadron Collider, and a major role they play indeed. And if you think back to some visionaries as part of the Square Kilometre Array project, convincing the South African government to support a bid to host the Square Kilometre Array, but also at the same time saying we have to build expertise. So what was originally Mercad 20, it was just 20 dishes, and it was, sorry, not Mercad, it was originally Karoo Array Telescope, and it was going to be 20 dishes. And then that turned into Mercad 64 dishes. But the idea is to actually build something, and build expertise. So the mantra that Justin and others often repeated was build it and they will come. But alongside that is build it and you build the human expertise. So if we really want to participate in these facilities that will be here in the coming decade, and they will win Nobel Prizes, we have to know what will Africa's role be in all three of those VLBI arrays. All right, so I want to thank you very much for that. I know there was a lot covered. I look forward to covering some of them more in the Q&A, but I now want to turn to Inian, who's going to tell you about this beautiful image and some of the science done with it. But before it comes on, I just want to show what an exemplary, just a spectacular example he is of the kinds of expertise that have been developed on the continent en route towards Mercad and Square Kilometre Array, and now allowing him to participate in the Event Horizon Telescope. He will sadly be leaving us, but joining Harvard, for a position he'll start there towards the end of the year. That's the kind of expertise that we're developing alongside a very exciting project like the Event Horizon Telescope. And I hope that we broaden that on the African continent very soon. Inian, over to you.
Hello, everyone.
Rather back to the or maybe perhaps back to the program director. I don't know. Apologies, Michael.
It's all fine. Let us enjoy Indian as long as we have him with us.
Thanks, Roger and Mikhail. Let me just share my screen. Yeah, hope you can all see my presentation. My name is Inian Natarajan. I'm a postdoctoral fellow at the WITS Center for Astrophysics at WITS University. I've also been associated with Rhodes University and Sarajevo. I've been worked closely with the teams there. And so basically, I'm just going to give like a short 15-minute presentation on the SAGISTAR results that were released a couple of weeks ago. I'm just going to talk about the algorithms and the data analysis that went into it. So here's a short overview of what the collaboration has achieved. So this is the night sky, and then in the foreground you see the South Pole telescope, it's located at the South Pole, and so this is the night sky that you see, and you increasingly zoom further and further into it with like better and better telescopes. Finally, we are able to see what's at the very center of our galaxy, which is the supermassive black hole Sagittarius A star. And it's only like 3 lakh minutes across, which kind of gives an idea of, just puts everything into perspective. These are the telescopes that participated in the 2017 SAGISTAR observation campaign. So there were 8 stations located at 6 different locations on Earth. And together they constitute the Event Horizon Telescope Array, which is a global network of radio telescopes. Here's a quick overview of how the whole thing works. So we always talk about like creating an Earth-sized telescope. How do you create an Earth-sized telescope with just a few antennas that are distributed around the world? So what actually happens is the signals are received at the different telescopes, they're digitized, and they're saved onto hundreds of hard disks. And petabytes of raw data are then shipped to a central facility, like literally manually shipped on aeroplanes, and they're all taken to a central facility where the correlator is located, which is basically like a big supercomputer which combines the signals from these different telescopes, so basically in a way that it acts like an Earth-sized virtual mirror. And then we use algorithms, certain algorithms called calibration algorithms, to find the weak signals that are hiding in the correlator output and remove all the effects of the atmosphere and the instrument so that you can only see what's there in the sky. And then finally, this calibrated data are converted into images using imaging algorithms or imaging techniques, which try to find the best image that matches this calibrated data. This, in short, is how VLBI is done. So the first step in this process is to do the calibration itself. So the collaboration used two different calibration pipelines called the HOPS pipeline and the CASA pipeline known as RPCAD. These two efforts led by Lindy Blackburn and Michael Janssen. And you don't really have to look into the details, but it just like removes the whole process, removes the effects of the atmosphere and whatever is in the intervening interstellar space between the black hole and us, and the properties of the instrument itself. So all these effects are removed, and finally you get data, the final data product, which basically look like this. So these are still numbers. You can just plot a bunch of graphs and try to gain some insight into them. But these also need to be converted into images. And that's the process that comes next. But quickly, from these graphs, we can get a rough kind of idea of what kind of models could give rise to this kind of data. And we see that the amplitudes are well described by a 50 microarc-second ring model, so that's a good sign. And between the two calibration pipelines, CASA and HOPS, we see very good consistency in the data. So then we move on to imaging. So EHT has been doing this since back when they released the M87 data. So there were 4 different imaging methods that were used. The first was DiffMap, which is inverse modeling, which is how imaging has been traditionally done in radio astronomy. And there are 2 new forward modeling methods, or regularized maximum likelihood methods, which are called EHT imaging and SMILey. And then there's also a fully Bayesian, a fully statistically robust imaging process. And for that, we used a software called TIMIS. And these are all led by different people located in different places in the world. And each of these software packages were developed by large teams. So this is really a work of 300 people. And these software packages have been vetted with synthetic data, which are simulations of the sky before the actual data were analyzed using these imaging methods. And the M87 results were released in 2019, have been confirmed by independent experts. Earlier this year, like a few papers came out where people using different methods have also found the ring. So that's a nice thing. And so this is something that the EHTC has really pioneered, this multi-pronged redundant approach to data analysis, where like everything kind of cross-checks the results of everything else. And the wisdom gained from this can be applied to other large-scale and high-profile projects like SK and Mercad, since this affects all of radio astronomy. So why did it take 3 more years to release images of Sagittarius star compared to the images of M87 star? Because those came out in early 2019, but we are now in 2022. So there are 2 main effects that we need to take care of while looking in the direction of Sagittarius star, because it's located at the center of our own galaxy. So we are looking through gas and dust in our own galaxy. And also there is the fact that Sagittarius star is more than 1,000 times smaller than M87. So the material that revolves around Sagittarius star does so faster, so that the appearance of Sagittarius star can change on timescales of minutes. And these effects manifest as the following two effects, which are interstellar scattering. So the gas and dust that lies between the black hole and the Earth, what they end up doing is they either make the image blurry and fuzzy. So that's the diffractive and refractive scattering. So either see like some substructure that you're not sure whether it comes from the intervening medium or whether it comes from the black hole itself. And also there's an angular broadening that can happen that can kind of make you measure the wrong sizes of the thing. So so mitigation processes for these needed to be developed and tested. And so there were a couple of techniques like introducing a noise floor for refractive scattering, and then the deblurring procedure was done for to mitigate diffractive scattering. So in the end, we tried to make the image less blurry and less fuzzy. And the other fact that the Sagittarius star is like 1,000 times smaller than M87 manifests like this. So here you can see in this video how the brightness of this source changes over hours. A typical observation takes about like an entire night, and throughout that night you can see the brightness like dimming and brightening again. So that's the flux variation, and there can also be structural variation over time, and these also needed to be mitigated. And there were a couple of procedures, especially this variability was modeled using certain physical and empirical criteria, and we tried to mitigate for the variability that way. So when all is said and done, so all the different imaging methods, after having mitigated for all these conditions, finally arrived at a whole host of images, tens of thousands of images, which are all averaged into the one image that you see at the top left. But these images don't all look alike because they depend on the different settings that go into how the imaging process is done. So, all these thousands of images can be clustered into 4 different clusters or 4 different modes, depending on the morphology, which is basically where you see the bright points around the ring and how bright each section of the ring is. So 3 of these ring clusters, 3 of these clusters are ring clusters, and that constitutes more than 98% of the images that were created. There was only 1 non-ring cluster, which is less than 2% of the images, but what's common among all of them is they do not change the size during the measure. All ring images have a diameter of about 50 microseconds. So, and there were also a whole host of tests that were done to check how the scattering mitigation affects the results and whether calibration using different pipelines change the results in any way. But the takeaway from this slide is that the different scattering mitigation schemes that we use does not affect significantly each image cluster. And also, regardless of which pipeline you use to measure data, you can still get the same average mean images in both the scattering mitigated and non-mitigated set of data, which is really it's really which really motivates us to believe that that what we are seeing is real. And so now we have the images, and there's also another approach that we can take where you basically try to fit different models to the calibrated data. So here again, what you can see on the top right is that from the graph on the top right, for the engineers and the scientists in the audience, you can see that the ring-like morphologies fit the data much better than other morphologies with the same number of parameters when you do the fitting. And we also quantified these morphological parameters using both geometric modeling and image domain techniques. And that's what you see on the bottom left, where there were 2 different types of geometric modeling techniques, the snapshot and the full track modeling, and then the imaging, where so each square that you see corresponds to each imaging method, 4 in total. And we recover a ring diameter of 51.8 microseconds with the ring thickness constrained between 30 to 50% of the diameter. But the other morphological parameters, such as the depth of the central brightness depression and the orientation of the bright spots on the rings, they're poorly constrained and depend on the measurement method. And this is something that we hope to get a much better information on as we analyze new data and develop new methods and have more telescopes, as Roger and Michael have mentioned. So we also want to, we have these images now, and we have the diameter measurement, but we want to relate that to some physical properties of the black hole. And so there is something called a gravitational radius, which determines at what radius around the event horizon can you start seeing the emission, which contributes to the ring that we see. And so all we need from this slide is that all the different modeling and imaging methods that we have, so the different colored curves correspond to the different modeling and imaging methods, and they all are quite consistent between each other, but they all have large uncertainties as well. And this happens due to the model flexibility that was needed to capture the variation in the structure of the source, and also the broad morphological diversity of the simulation suite that we created, since we don't know the inclination of such a star. It is much less constrained than the M87 star. And using these measurements, and also using independent measurements of the distance to such a star, we determine the mass of such a star to be about 4 million times the mass of the sun, which are very consistent with some more precise constraints that have been obtained from stellar orbits using the Keck and VLC telescopes. These have been published by independent teams previously. Those are the vertical colored lines that you see in the graph. So we are confident that we are doing the right thing and we are getting the right results. So we also want to test astrophysical models of this supermassive black hole. There was a large library of source models that were created by the theory team within the EHT collaboration. These constituted general relativistic simulations and other geometric models, and there are various other aspects of black hole emission. And all these models, so there were about 200 models in total, these were all tested against 11 observational constraints. Our 1.3 millimeter observations with the EHT, and the fluxes that were retrieved using multi-wavelength observations, and also some variability constraints, such as star. But none of the models here actually passed all the constraints. These models were all too variable. If you set aside variability, then a certain set of models satisfy the remaining 10 constraints, which in itself is remarkable. And these models tend to fall into the category of between mad and sane, where basically you kind of propose the accretion around the black hole is arrested by the magnetic field. So they fall in that category, and we also have reason to suspect that these all have prograde spins, meaning that the black hole is rotating in the same direction as the material revolving around it, and they also expect it to have low inclination. So yeah, we are looking at the black hole more edge-on than we expected. Sorry, face-on than we expected. But we need to improve the quality of our images here. The passing models also predict the existence of jets, but we haven't observed any jets yet. But this motivates further studies, multi-wavelength studies, and also with more stations, as Roger had mentioned earlier. So we are looking forward to doing this analysis. And yeah, finally, I just want to mention about tests of gravity. So we have some data using like the gravitational wave data from LIGO and Virgo on stellar mass black holes. And now we have data from the EHT on M87 star and Sagittarius star. And what you see on the right here is that the gray strip is where the observations indicate that the models rotate from what, the models deviate from what general relativity predicts. So what GR predicts is that any astrophysical black hole is entirely predicted by its mass and its spin, or its angular momentum. This is called the curve metric. And what you see is how much the observed data give us reason to believe that there is deviation from this metric. But even though the masses of these stellar mass black holes with LIGO and the supermassive black holes with EHT span 8 orders of magnitude, all observations are consistent with the expectations from GR and also lend support to the current nature of the spacetime. And you'll hear more about the theory from Andrew. And yeah, I just want to finally leave you with this. So the central black hole in our galaxy was discovered in 1974, almost 5 decades ago. And a lot of work has been done over the past 5 decades. And finally, this year, we have made the first image of Sagittarius star. But this is just the beginning, really. I mean, this is only going to take off from now. Thank you very much. And thanks for giving me the opportunity to present.
Yes, thank you very, very much, Inyan, for this not just very nice, but also very enlightening presentation on what is actually in that image, where, well, we usually just see those one image in the front, or hopefully front cover of newspapers, just to get an idea of how much work and how much checking and cross-checking there actually is involved, and how much physics simulations actually go into just having this image is quite remarkable. I guess we will hear even a bit more on that particular part in a little later talk. So now I have the pleasure to very briefly introduce to you the latest status of the Africa Millimeter Telescope, as was already introduced by Roger so kindly. Let me try to share my screen, and I hope you can see my slides well. So, as I mentioned before, I'm based at the University of Namibia, but also affiliated with Northwest University in South Africa, and also a proud member of the Global Young Academy. Obviously, today we talk about the image of Sagittarius A star, the black hole at the center of our galaxy, and I will not repeat. Don't be afraid. I will not repeat all what Roger and his colleague have told us before, but I want you to take away from this slide this very image here, which is centered with the telescope stations around here, which is centered about Southern America. And that is so for good reason, because, well, what you see here is not having a telescope in Africa. And I want to very briefly only bring us to the image that was released 3 years ago of the Galaxy M87 that we all have seen a few years back. But also there you see that there's a big hole in this network of telescopes where you see them from the South Pole close to the North Pole, at least up to Greenland. You see particularly from Hawaii to Europe, all the continents being included there, but you see that there's not a single telescope here in Africa so far taking part. And then let me very briefly, Roger mentioned a couple of times the geographical advantage that we have here. Let me very briefly introduce two of those aspects. They're a little bit more true for other parts of astronomy, but they're very much true as well for these types of observations. And that is, on the one hand side, that as you can see here in this night sky image of the Earth, that Africa, particularly compared to the US and to Europe, is a very dark continent. You see here below up, where you just see, well, the major Gauteng region, and in Namibia, which is highlighted here, the outlines in red, you see essentially the capital Windhoek and a few more cities around, but you see there's not much light pollution around. And in addition, what I want to show you in this slide is that for as much as we here in Southern Africa usually and rightfully complain about the rather bad conditions for agriculture and farming, which is caused by having not much rain, and well, with that comes not much clouds. So you see here the average annual cloud cover. So blue regions are very cloudless regions, red regions are very cloudy regions. And you see here Southern Africa with Namibia and South Africa mostly is one of the most cloudless regions in the whole Southern Hemisphere. And with that, I want to very proudly quote the then South African Minister of Science and Technology. Although the ministry got slightly renamed, as you all know. And I don't want to read the quote for you. I'll leave that for you to read yourselves. I just say my interpretation of the words of Honorable Naledi Pandor at those times when she visited Windhoek, where, well, there are a couple of problems that we have in Southern Africa. That's true. But we also have some areas where we have an advantage, and we need to grab these chances, those opportunities where we have advantages already, and make good use of them. And as outlined before, astronomy is one of those points where in Southern Africa particularly, we have quite some geographical advantage to make good use of. So I want to just very briefly bring to you the map of the region here, where you all know we have the Southern African Large Telescope, we have Mercad here in South Africa, we have sort of behind the picture of HAS, the Hartbees Soak Radio Telescope, and we have the HAS telescopes here in Namibia, where the capital Windhoek is highlighted here, where the University of Namibia's main campus is. One word about HAS, I will, contrary to what Roger said, not introduce it much more, but it is a world-leading instrument in its field of gamma-ray astronomy, and it will celebrate later this year its 20th anniversary, so being in operation for 20 years here and doing world-leading science as well. What I want to highlight here is literally, as you can see on this very picture at the HAS telescopes, 30 kilometers from there is a very nice table mountain that is called Hamsburg, and that has for long been foreseen to be a place to do astronomy from. And you've seen this very picture from Roger before. There currently is a smallish, 70 centimeter amateur astronomer's instrument. And what we want to do is we want to bring a 15-meter radio telescope up there. But quite obviously, this is not to scale, and we want to call this the African Millimeter Telescope. We intend to reuse the Swedish ESO telescope, in short CEST, which is standing in Chile currently and is not being used there anymore. But we want to have that completely refurbished. So it will, in the end, rather be a modern telescope in the NOEMA style, so as the European station NOEMA. And we want to place it on, well, as you can see, this very nice 3 × 1 kilometer plateau in the very arid region of the country. You've seen a very similar simulation of baselines between telescopes by Roger previously, and I just want to highlight one point here, which comes in addition. You see the additional baselines by the AMT highlighted in red, and the crucial point I want to make here is that, well, with what we call a Western array, you see with a lot of yellow lines, you already can do pretty good imaging right now. But with this, what we call Eastern array, which is mainly made up by the European stations and the upcoming, well, not yet being there, African Millimeter Telescope, is currently not so well possible to do images of the black hole at the center of our galaxy. And that's exactly one of the reasons why we want to build a millimeter telescope here on Mount Hamsburg. On the left-hand side, just very briefly, you see in blue here sort of the current situation. This is a plot of time as the Earth rotates. And on the other axis, you have some, say, arbitrary measure of image quality. And you see this dashed line here, and only if your image quality is above that line, you can do actual imaging. And you see currently with all the Eastern array, so for many, many hours, you cannot do imaging only until some of the Western telescopes can see the source, and then the imaging works quite well. Whereas with the addition of the AMT, and this is then depicted here in the red line, you see that quite a couple of additional time slots will become available for imaging, literally doubling the time for doing images. And just to get an idea, so for just the eastern part of the array, if this is the simulation, this is what the current array would observe. And with addition of literally just one telescope, the AMT, this would become better. And quite obviously, following Roger's line of thought, the more telescopes, the better the quality, and particularly also with more than one telescope on the continent here. I don't want to run through this very slide. I just want to tell you that while there is more science to be done with the AMT than just the EHT VLBI, but there's also another network of radio telescopes, which is called the Global VLBI Array, that we want to participate in. And there is also, and let this not be forgotten, there's also still the plan to have centimeter VLBI on the African continent, which was always dubbed the African VLBI network. And the AMT can play a crucial role in that as well. What we're currently in is, well, not just a science project, but we also want to build capacity, as was highlighted by Roger as well. And so we want to have the whole project running through different steps of careers of learners, so to say, initially learners, later scientists. And one of the aspects particularly aimed at school kids is that we have a mobile planetarium in country. We just literally 2 weeks ago have had training for operators of this planetarium, so that in the very, very near future, we can have regular school visits with this planetarium to just engage with school kids and the wider public, and to make astronomy more accessible to them also during daytime. And we have, as Roger also mentioned, a very first PhD student, which is funded through the AMT project by the support of our international collaborators, as listed here on this slide. With that, I just wanted to very briefly mention that the AMT also has made it into the public media, and you might have seen that there was capturing on Nature earlier this year, which was initiated by Radboud University, making available the first 12 million euro to the group of Heino Falke for this very project. And so we hope that with that as base funding, will convince other funders to also make the rest available. Also, very recently, we had a capturing in the Popular Science magazine, which has quite some international reach, and also trying to have everyone involved. You see a few pictures here for signing memoranda of understanding here, for example, with the Vice Chancellor of Radboud University and our Vice Chancellor at UNAM. And also from earlier this year at the AU-EU Summit, the colleagues from Radboud University met our president, Dr. Hage Geingop. With that, I just want to close you and leave with you just a slide with the supporters of the project. They are so far. And let me at this stage also mention that quite currently, together with University of Pretoria, I have the honor to host an Sarao funded master's student to look into the site investigations and site characterization. Thank you for that. And I will stop screen sharing just now if I find the button. So with that, I want to give over to the more theoretical work on the black hole shadow and the constraints for the general theory of relativity, and would ask John-Drew Brink to please share her screen. John-Drew, we see your slides.
Can you see it? Perfect. Okay.
Yes, we can see it. We can hear you. Thank you. Please go ahead.
Do you want to see me too? Can you see me as well?
We can see you as well. All perfect.
Okay.
Thank you.
So the first is an apology. I upgraded my computer and Zoom doesn't work on it at the moment, so I'm on my phone. So this is a bit of a new format for me. Firstly, thank you for the invitation of giving this talk. This comes with a disclaimer. I am not part of the Event Horizon Telescope. I have not been closely involved with the analysis. I am, however, very interested in testing general relativity, and I've played with some of the stuff a while back. So what you're going to hear from me is sort of a experienced beginner's response to what the results are, as well as why I am incredibly excited about them. A tremendous amount of congratulations to your collaboration on achieving this. It's really wonderful. It's something I've dreamed of for well over 7 years and longer, I guess. So I'm very, very pleased. And it's great to have South Africans involved with it. What I am going to do is, I was wondering how to start this talk, and I wrote the whole talk, and then I went and checked up on the spins of black holes, because it has some very interesting implications that I might discuss. And I couldn't find, I have this little list of various spin estimates for Sagittarius A star that have developed over the years. And I couldn't find it, but what I did come across was a paper I wrote with Marissa Geyer, and who's currently the commissioning scientist, South African, at the SKA, and Tanya Rehinderer, a colleague, well, that's currently in Germany, in 2015. And what I want to say, I don't know if Marissa is in the audience, but Marissa, congratulations. You had the EHT grade your master's project and you got full marks. So I just want to read an extract, and it might be interesting for the collaboration as well, as I will come to mention very briefly in the end. So this basically thing was explored, what black holes were like and how resonances would occur around black holes. It was a perturbative study, so it's not modeling. There's no fancy images. It was pen and paper. What we did was, however, suggest a robust method of determining the black hole spin. And there was sort of a small example towards the end where it simply said, based on previous results from monitoring the SAG-A, that saw an indication of time variable structures at a certain radius. And then images, we didn't have images, it was extremely blurry. Based on the calculation that was done in this paper, we went on and we predicted that SAG-A spin would be prograde, and suggested that the spin would be 0.5, which is entirely consistent with the results that are coming out, or my understanding of the results that are coming out of the EHT. So Marissa, very well done. What I am going to do is mention a little, now that we actually have images and with some of the things coming out, I'm going to say how some of these results might be useful in the future. So I want to say, I told you guys so, but it's very nice to actually have some of the analysis vindicated. So it's well worth, this is not a complicated paper, it's a beautiful paper, in fact, but it got the prediction right. So what I'm going to do now is start talking about constraints on GR, but mainly I'm going to talk about some very exciting science that is also possible with the Event Horizon Telescope results, And it's going to be an attempt to basically make it accessible to people like me that are outside of the calibration, that are being confronted with some of these images for the first time. So I was asked to talk on constraints on GR. The short answer is none so far. It's a tremendous vindication of the theory, and it's a second direct observation of the existence of Event Horizon. It is literally a huge thing. The Event Horizon Telescope does rule out a number of alternative theories, but my comment on that is that those theories are so far-fetched, I thought that they were highly unlikely anyway. But you do have to start somewhere. I have had so many people trying to test GR. It's a field that started with a few of us, and then St. LIGO, it's exploded, that I've developed a very effective BS buster for when a theory is actually saying something, or when an experiment can actually say something. And the thing simply goes, look at the numbers that are important, the mass, which the Event Horizon Telescope is fixed, look at the spin and determine what it can say about that. Then you need more numbers before you can actually say something else. What I am going to do is sort of use this sort of quote of the little boy that I picked up from some kid's book. The amazing thing when a child tries to rule out the hypothesis of having a dragon under his bed is that he develops enough courage and ability to peek out from under the sheets and obtain a clearer view of the mess underneath the bed. Okay, what the Event Horizon Telescope has done has removed a lot of the obstruction to viewing directly into the Galactic Centre, and has opened a playground that we will be exploring for generations to come. Okay, so what I want to say is there's a difference between, mainly for the students, there's a difference between testing general relativity and determining and exploring the matter content in the geometry. Okay, you ask those questions within general relativity. Okay, and for this latter thing, and testing general relativity ultimately as well, the Event Horizon Telescope has a slew of very, very useful tools. Before I comment on some of the other results, I want to look, we've seen some of the images, but I just want to reiterate some of the ideas that I'll be using. Firstly, if you have a light source on the black hole, and unfortunately I don't have a pointer on this phone, that emits several rays, the geometry around the black hole simply bends the light. So this is just a simplified view because I want you to try and understand how this eventually translates into the image. So light travels in straight lines, we all know that, except if it goes close to the black hole. And if it goes close enough, 3M of the black hole, it actually can go into an unstable orbit that we call the photon sphere, that is an orange circle in this image. Okay, and you can then work out the angle of that photon sphere, and that's simply the angle where light will simply be captured by the black hole, all the other light will be radiated to infinity. Typically, when we talk about the event horizon in some units, which you'll be seeing because I'll be comparing a number of things later on, we have 2m. The circle that the light orbits around is at 3m, where m is some unit. And so that is simply what happens if you have a single light emitter near the event horizon. A telescope is a different thing. A telescope, you sit down at this green dot on the right, and you have a whole bunch of light rays coming to you that you then use to make the image. And what the shadow is, or the angle of the shadow, is there will be a region, if there are no emitters between you and the black hole, indicated by alpha SH, an angle, an opening angle from which you will receive no light because the black hole blocks it. Okay, what is, however, interesting is that the images we are looking at when we look at these black hole shadow images are much, much more interesting than simply looking straight at an ordinary image. And it takes a while to get used to them because the black hole acts as a lens. It's like if you look at a book and you've just put it a very large distorted eyeglass or your grandfather's magnifying glass on the book, it looks different from what you would have expected. And I want to give you some feeling of what that thing is like. So what I'm going to do is, let me now go about, and I'm a theorist, so I'm going to have a black hole scruncher, and I'm going to say, what happens if we turn Saturn into a black hole? Okay, so Saturn has a disk around it. Its disk structure is dependent on the oscillations in the black hole. And if you take Saturn, which currently has a radius of 58,000 kilometers, and you squash all of its mass into 85 centimeters, which you could try and put under your bed and destroy the Earth in the process, then that is the event horizon of Saturn if you squash all its mass into a black hole. What's going to happen then is you're going to have a radius where the light, the photon sphere, where the light orbits around that little 85 centimeter black hole, is going to be 127 centimeters. And then if you want to work out what the image looks like, you have to go to each and every point of light on the disk around Saturn. You have to work out how that's the Saturn black hole, and you have to work out how that light is going to bend before it gets to you, and then construct the image that way. Okay, so for Saturn, once again, the calculation that you could work out for this little Saturn black hole, you can work out that the angle of the shadow, in other words, the angle where if all the light sources are outside the black hole, you won't get any light from, for Saturn here is 220 centimeters divided by the distance you are from the black hole. Okay, so let's now have a look at what this image is going to look like, and let us have a look at suppose I have a Saturn-like black hole. In other words, I have a flat ring around the black hole, what it would appear like, and how many of these models were actually built. In other words, you have your flat ring, you work out how light will travel for every single emitting object inside of the black hole, and what you're going to get is, I'm going to show you on the next slide, but when I go to the next slide, I want you to know that the thing that you have actually imaged, at least on the first slide, is a ring-like, the Saturn-like object where the ring is like edge-on. Okay, so I want to give you a feeling ultimately of what the images mean. So if you look at the Saturn-like object, the image I'm going to give you, the distorted image that we'll see, is the top image. Okay, so this is the physical arrangement of the particles. This is the arrangement ultimately of the light. Okay, this model was used as it's an exact model that was calculated for Interstellar. It's a black hole that was in that science fiction movie, and I was part of the group of simulating extreme space-times that did the mathematics, and the visual effects were eventually done by Double Negative, which is a whole bunch of artists that do a lot of these big budget movies. So look at this image. What we are seeing here, this front part, the image basically has something that looks like a disk, but then it has a ring around another smaller fine ring. And the way you interpret this is the back ring is the top image of the part of the disk that goes behind the black hole that has been bent, or sorry, the top ring is the image of the back of the black hole that has been bent so you can actually see it. Okay, so just the Newtonian view, this thing would have been hidden behind the black hole, but the black hole, or behind the planet, but the black hole has actually bent the light that you can see it on top. The lower part of the ring is actually the image of the lower part of the disk that has been bent round and that you can now see below. Okay, so when you look at the circle around the central back object, that is not the orientation of the disk. What you are seeing there is the image of the disk bent around the black hole. In the front part, you have this line, which in fact is the disk, which is lying in the equatorial plane. Okay, so one of the big things that you want when you want to test GR is you want to know the mass accurately, you want to know the spin, you want to know it accurately, and what is often not mentioned is you want to know the orientation of the spin as well as magnitude. Okay, and so one of the potential things that the Event Horizon Telescope makes me so excited about it is you can actually start determining that for our black hole for the first time. It's harder with Sagittarius A star than with M87, because with M87 you have a jet that often gives an indication. Sagittarius A star doesn't have one, but you can attempt to determine what the spin will look like, or what the orientation of the spin is, by looking at the image itself. Okay, and to understand this, this is the same disk. Well, this is not the Saturn disk. This is a disk that is some of the earlier theoretical work that is simply what changes in the figures across from left to right is the inclination angle. In other words, how you are looking at the black hole, whether you are looking at it down the spin axis and whether you are looking at it from edge on. So the object on the right is simply the image that I showed you, the fancy image I showed you previously. And as you go to the left, you are looking more and more from above. If you look at it directly from above, you'll actually be able to see just the black hole and the disk itself. There will be very little distortion of the disk, okay, because the light from the disk will be coming directly at you. Another important thing, if you look at these images, is that the way the black hole spins will also influence the light you see. Black holes pull things around them to spin around them. And sometimes if you have a prograde disk, that is, in other words, a disk that is spinning that has the same spin as the black hole, it tends to pull in things closer to itself, whereas a retrograde disk tends to push things further away. And so below is, above and below on this image is comparisons between disks, a black hole that is not spinning, and the one below is one that is spinning. Now, there are a lot of reasons why we expect disks mainly to have the same spin as the black hole, because often the disks and possibly the black hole are formed once the black hole forms, or there are mechanisms that are coupled in their formation. And so that was the reason why in that paper we suggested that the disk would actually be prograde. Okay. So here I've just picked up the things I looked for. So when I started looking at these results, I went through and I just as a beginner went through and thought which ones I actually believed, which ones I thought are model dependent, and which ones which results I was really happy about seeing. So this particular case seems to be two images. The one is taken from an inclination high up, basically looking down on the disk. And the other one is taken from an inclination sideways, sort of like the big gargantuan example I gave you, or gargantuan, the black hole that I gave you. And I just want you to have a look and see how the images are different. And in this particular case, the analysis goes about and it says, this one is consistent, or the one that is basically looking from the top is consistent with the radio observations, and the other one is not. Okay, so for at least testing GR and looking at some of the astrophysics, the orientation of the disk is very important. And these are some of the first attempts to actually fix it rigorously for Sag-A, which is incredibly exciting, because there are a number of puzzles that are associated with the spins of the black hole as well as the spin of stars around it. So, and to give you one of those puzzles, I have to introduce the S stars. Okay, so the S stars are a bunch of stars that spin around the black hole. So let us just orientate ourselves. If you look at the image on the right, we're in our solar system. We were in one of the spiral arms of the galaxies. Our galaxy has a very flat, clear galactic plane. And Sagittarius A star, where all the fuss of this lecture is about 26,000 light years from where we are currently. Okay, so that's the light, the distance the light traveled. in some of the previous talks, people are so entrenched in what on the details of what they achieved. It is amazing to wonder simply at the feat of what was achieved. The image that was created with that Event Horizon Telescope is about akin to being able to see a donut on the moon. Okay, the angular sizes and the resolution attained is very, very impressive. It's an immense achievement. Really, congratulations, you guys. Okay, so here is the image. It's a tremendous distance we're looking over. And to just give you an idea of where we look at it, if anybody looks up at the night sky, you'll see the Galactic Centre. It's the Milky Way. And then you can look for the teapot, which is Sagittarius A star. You see the constellation over there. And the place where all the fuss is about is indicated by that arrow. It's the rotational core of the Milky Way. So every single star, our own solar system included, are rotating around Sagittarius A star. And what this previous result seems to predict is that one of the preferred spins currently consistent with the data, or the spin selections consistent with the data, and I didn't see there was a dearth of error estimates on some of the results, which I think the collaborations were cautious with the first announcement, but I would actually love to see them, is that there are several images that actually appear to have a reasonably high inclination view of the black hole. In other words, we are not looking necessarily at it in edge on, but we are looking at it sort of more from the top. And what that basically means is that its inclination angle, because we're looking in through the Milky Way, each inclination angle, its spin axis seems to be aligned with a galactic plane, rather than my naive idea, like with the case where Saturn is, where you have your spin axis basically orthogonal to the plane. Okay, the other unusual result that I found surprising was that, well, surprising until I went back and looked at my own prediction, is that it's spinning fast, that expected spin of 0.5 or dimensional spin of 0.5 is a fast spin. Okay, so what you now have is a black hole that is spinning with a spin orientation strange compared to the galactic center. They're not aligned. And one of the puzzles are, firstly, once I verified how sure you are of this, is why. Okay, but the puzzle gets even more interesting. Okay, and that's where the S-stars comes in. So the S-stars are, before the Event Horizon results, the way in which Sag A star's mass was determined. It's a whole bunch of stars that orbit it with about a period of 15 years. And if you watch these orbits very carefully and you do the orbital dynamics with NGR, and you'll see that the orbits don't close, they precess slightly, and that precession rate can be used to determine the mass. And several of these stars agree that the mass is something like 4.1 million solar masses or 4.3 million solar masses. So this was actually the subject of, as somebody else said, a previous group, but it's also a previous group that I admire very much. It was the 2020 Nobel Prize for some very solid work around Sag A. And here are some of the orbits, the initial orbits for which they got the Nobel Prize. Just if you look at this image and you compare it to the Earth's orbits, which is shown in the bottom over there, they are almost comparable in scale, but you must remember that these lower orbits on the bottom right are orbiting the sun, which is 1 solar mass, and these other stars are orbiting 4.1 million solar masses. Okay, so they are really relativistic orbits, these other ones. And so one of the puzzles are, remember in astronomy, if you look at an image, it's very hard to determine the distance from you. So it's very hard to determine the orientation of these orbits in 3-dimensional space. But people have tried this, and the prediction so far is that those stars cluster themselves in basically 2 S-star disks. So this picture on the right is once again a fuller set of the orbits that are available. And the image on the right, and this comes from a discussion by Abram Loeb and collaborator, are the just a schematic of the orientation of where in 3-dimensional space relative to the galactic disk. So this green thing is the galactic disk. We are lying somewhere in the galactic disk. The spin, some of the Event Horizon Telescope results suggest the spin of SAG-A lies within 30 degrees of the galactic disk. Okay, and that is at an angle with these S-stars. That is a very big problem. It's not a stable structure. And so there is still going to be a theoretical fight to try and figure out how to make these results consistent. Okay, because the S-star results are, people are confident about. The SAG-A star results have come in. And the problem is that if you have SAG-A's spin orientation lying at such an angle with respect to the S-stars are close enough that the space-time of SAG-A actually starts affecting the orbits. And if the spin is large, that effect gets bigger. Okay, and the orientations as they are now also implies the spins are the effect on the orbital plane of these stars orbiting SAG-A is also going to be large. Okay, so this structure is an uncomfortable one with all the results coming in, and it's one of the puzzles that are going to be sorted out in the years to come. And in fact, as part of the question period, I would love to hear your opinion on some of on this problem. Just so that's one of the things I immediately picked up that got my interest. The final comment I'm going to make just from looking at the papers is there's a lot of comment in the data analysis about the source variability of SAG-A. And there's a lot of attempt or a lot of comment on how you average out to try and get the image. You have to try and get rid of the source or average out the source variability. My comment is I view this as a feature, right? The prediction that Marissa made and Ms. Marissa and Tanya and I made was entirely based on estimate or on source variability. And what we did, and this might actually be useful in establishing which frequencies are coming from the black hole itself and which frequencies are coming from the instrument, and possibly design observation filters on the basis of it, was we simply went about and we said we wanted to make a disk. We wanted to build a disk around SAG-A similar to Saturn's disk. And now if you go back and you look at Saturn's image, the disk structure around Saturn is built up by a lot of bands, but those bands are actually coupled to the dynamics inside of Saturn. And so we looked at SAG-A and we did small perturbations. We said, suppose the space-time is a small perturbation from SAG-A. What frequencies do you expect to see in a disk? And how are those frequencies coupled to the actual position in the disk? And so it's a perturbation study. It's not dependent so much on a specific model. In fact, it will be true for any model departing not strongly from SAG-A or from a black hole, which is what seems to be confirmed that SAG-A in fact is. And the model that we came up with is that you would have a series of bright bands having a distribution such as what we see in this image. And then we went on and we calculated the frequencies of all those bands. And the paper that I cited right at the beginning has a partial list. I've subsequently got a complete list, and they may at least serve as a potential method of filtering out of and sort of helping to sort out variability problems and what might be due to the telescope and what may be due to SAG-A. So what I'm going to do is I'm going to leave you with this image and just possibly flash the frequencies that we actually expect to come from merely perturbing black hole or orbits around the black hole results, the nice thing about it is that they are very easy to calculate. You don't have to make an image. You don't have to go through a supercomputer and have your, in some sense, argumentation inaccessible to people outside the collaboration, which is one of my criticisms for some of the discussion of the results. They're hard to check if you're not in the collaboration. You can calculate it yourself, play with it, manipulate it. So the one thing I can look at, if you look at this trumpet shape, what is depicted there is an indication of the potential well of the black hole, right? I said the black hole distorts the space-time, and what this thing indicates is simply I gave an indication of what the distortion is like. So you can see it's like this idea of your rubber trampoline. You put a heavy object in and then you're going to distort it. Right inside here is the event horizon. As you climb out, you're going to get several of these resonances, and the one that the thing was predicted on, or the prediction was predicted on, is this 2/3 resonance, okay? And there's a lot of argumentation there, but what I'm going to do next is simply show you a prediction of the dominant frequencies that are going to come out in that potentially can be viewed in the Galactic Centre. That is not the result of complicated modeling. It is simply the result of perturbative properties of the black hole. And it would be fascinating to actually see a frequency spectrum of the results coming out and compare it to, say, the last column, which is 10⁻⁴ hertz, or if you actually have the time period, it's a central one, and see if there are more of the things that we can resolve rather than the argument on which Marissa and the rest of us actually predicted what the spin would be like. So in conclusion, I totally believe the spin results. I'm very, I think they are true. There are puzzles with orientations that are coming out from the results, and I'm sure those will be resolved in time, and I'd love to hear comments about them. And congratulations on a tremendous result. And I think that's all for me.
Thank you so much, Giandru. I think that gave us a very good background of the theoretical background that makes up all these, well, not makes up the images, but makes up all the bending of light, which leads to the images that have been recorded. And thanks for so nicely depicting those for us here. With that, we come to, I would say, the nicest stage of the session, so to say, and that is the moment where all of our audience are having the possibility to ask questions. And just for the sake of housekeeping, for that, please do raise your hands. We will then call you and unmute you, or write your questions in the chat, or if you're following us not within Zoom but on YouTube, you can also please write your questions in the YouTube Q&A section directly as well. And as I see the first couple of hands coming up, let me call firstly Arun Kumar Bisham to ask their question.
Thank you very much. Firstly, the speakers gave very good talks. But what I would like to ask is, we've observed the supermassive black holes in M87 and also in our own galaxy. Do we expect to find supermassive black holes in virtually all galaxies? And secondly, having observed these in these two galaxies, what is likely to be the next candidate? Thank you.
I guess that can go to Roger.
Sure. Yeah, so really good questions. The answer to the first question is we actually have very strong evidence that there are supermassive black holes that lie at the centers of most massive galaxies. And by massive, we mean galaxies of order the mass of our own Milky Way and larger. There are all sorts of indirect methods which you can probe the inner mass distribution at the centers of these, and all the evidence that is built up over the last 25 years is that supermassive black holes lie at the centers of all massive galaxies. And in fact, it's deeper than that. They actually correlate quite strongly with the mass of the galaxies they live in. Now, in terms of getting more direct than that and actually imaging more supermassive black holes, the EHT is building up a large candidate list. But what we need is the largest possible orange donut on the sky, all right? And what we need there is a very massive black hole, and it needs to be nearby, relatively nearby. And M87 and Sagittarius star, the diameter there is approximately 50 microarcseconds, so of order 1,000 times smaller than an HST, Hubble Space Telescope pixel. Now, we can't just go after massive black holes, but they also need to be pretty bright at the observing wavelength of the Event Horizon Telescope. So the combination of the flux density at 230 gigahertz or 1 millimeter observing wavelength and the predicted apparent size of the shadow needs to be taken into account. And from there are a whole host of candidates, and the Event Horizon Telescope is at least members of the Event Horizon Telescope collaboration are using other telescopes to build towards doing dedicated Event Horizon Telescope observations to try and image these. But it's a very exciting era to now, having succeeded in these first two images and shown that the technique does indeed work, now adding stations and expanding the list of targets, both for shadows and for ancillary sites.
Yeah, thank you, Roger. With that, the next person to ask a question and to unmute is Yintse Ma, please.
Hello?
Yes, we can hear you.
Okay. Yes, great. Yeah, I have two questions. One is regarding the second speaker. The second question is about the fourth speaker. For second speaker, he displays a graph showing the three constraints on the deviation of general relativity, and I wonder what this delta mean. What is this deviation from GR? And I have another question to the last speaker, the lady. Yeah.
Yes, please go ahead. Well, if not, then let us start with Ininyan, please.
Yeah. So that graph that I showed basically shows how much the observed data deviate from the predictions of general relativity. It's called the fraction deviation parameter. This is something like someone like Jandru can explain this better than I can, being the theory expert. But so it's basically we expect these black holes to be described by the curve metric, and how much do these black holes do deviate from the curve metric is what they're trying to measure and estimate. And so with the EHT data that we have now and the gravitational wave data on stellar mass binary black holes earlier, we have this like the line, the gray strip that I showed, it just goes right across zero, and it's like cut through what we would expect from general relativity. So this shows us that, or this makes us more confident that these black holes are curved black holes, which are basically black holes that are.
Well, as far as I know, curved black holes has two parameters. One is mass, one is spin. And then what this delta is, what this delta means.
Sorry?
what does the delta means? What is the relationship between the delta and the mass and spin of the black hole?
Oh, sorry, I don't know the formula off the top of my head, but it's a parameter, yeah, that it contains like a few quantities. The formula for delta contains a few quantities that include the mass and angular momentum, and then that kind of gives us a metric for measuring the fractional deviation. You can find the whole derivation in, I think, paper 6.
Okay, and my second question is to the lady. Janu, yes, great to listen to a talk. And you said the spin of the black hole pretty much lying within the galactic disk, within 30 degrees. Will that will cause a problem of the jet being able to destroy the accretion disk?
No, not in SAG-A. So one of the differences between SAG-A and M87 is that they didn't detect the jet clearly. So in M87, what makes it very easy to fix the orientation of the spin is you make assumptions about the relations of the spin and the jet. And I think they're able to actually resolve the jet. Roger can correct me in M87, but in SAG-A, they weren't. So the inference of the spin in SAG-A is simply coming from the images. Okay, so SAG-A does have a light jet in some things that was observed a while back, but I don't think it was actually taken into account it didn't weigh, it's a very, there might have been ejector, it doesn't have a strong jet at all. So no, there's absolutely no chance that SAG-A is going to destroy the disk in SAG-A, or the jet is going to destroy the jet in SAG-A.
I can quickly just make two brief comments on that. If you're finished, sorry.
Yeah, go ahead. I can say something else about the deviation parameter, but finish first.
Oh yeah, that'd be really good. Let me just very quickly, just because since you asked, we don't really have, there's a hint of extension from the M87 image towards the ring to the jet, but it's really those shorter baselines that I was talking about, like you would have with a Southern African station linked to the AMT, that would help in actually pinning that, the anchor of the shadow to the jet. And then, I don't think there's a lot of debate on whether there's actually a jet with SAG-A. Obviously, the Fermi bubbles, the gamma ray emission on very large scales hints that, this long time ago there was, but at the moment, I think there's a lot of theoretical debate and why we need to improve the imaging as well.
Yeah, if there is one, it's very, very slight and very, very small. SAG-A is quiet. That's the other remarkable thing that we sort of gloss over. We're also keen on the image. The fact that the estimate of the mass of the S-stars that are sitting at about 1,000 to 10,000 Schwarzschild radii away from the black hole, that mass estimate is the same as the estimate you're getting from looking at the horizon itself, which is like 6M or something from the black hole. What that means is that there is very little between the S-stars and the black hole itself. And it's for the first time we've actually managed to pin that down, right? That picture under the bed of the dragon under the bed, what the gravitational potential well at the beginning, at the center of the galaxy, there are a whole bunch of theories that things can collect in there. I mean, it's literally a well. Things gravitate towards it, dark matter, a whole bunch of other things. And I've steered clear in that talk because the astrophysics, firstly, is pretty amazing. But this result simply is a very good bullshit buster for that. There's not a bunch of exotic objects sitting in the center of our galaxy. The fact that, and there's not a bunch of exotic things, two exotic things, between the orbits of the S-stars and the orbits of the horizon. And this is the first time we've actually been able to say that so conclusively. It is an amazing result from that perspective.
Yeah, thank you both for those extensive answers. I think we take one more question here from the live audience, and then there's two more from YouTube, or from the chat and from YouTube. So the next one is Ludwig Schwartz, please.
Hi, it's Ludwig here from Sarar. Thanks for the very informative talks. I've got two imaging related questions. The one is, Was it challenging to find the field containing the black hole, or was it pretty straightforward given its small size? And did you guys make a traditional dirty image of the field as well? Thanks.
Ian, you or me? Who should we take? Who should take this one?
No, I mean, you can take it. You can continue. Fine.
Oh, okay. Well, I mean, so Sagittarius stars are pretty bright source, so it's depending on the frequency, but it's of order of a few Janskys. So the astrometric precision is extremely well known, and it's been observed, from L-band all the way up to 230 in the lead up. So the astrometry was pretty well known. So knowing the field of view it wasn't really a problem in that light. Why have I gone blank? Oh, did you make a traditional dirty image? So the dirty image, I mean, there's so few stations that the Ludwig, you're the interferometry expert. So I'll kind of answer to you and then explain to the rest. But basically, the instrument response, the point spread function, to those in the audience, this is kind of the because we don't have a perfect Earth-sized telescope where there's glass everywhere, but actually you've only got small bits of glass spread across the Earth. You see a very fuzzy image compared to if you had perfect glasses. So if I had a whole lot of dirt on these glasses, I would see kind of a blurry version of what's in front of me. And that's the EHT has got a very blurry version of that. But yeah, there are two approaches. So one is actually traditional, making a dirty image, trying to clean it using, the 40-year-old clean method that Ludwig, very well. And then there are several forward modeling techniques. And then there's also just direct modeling in visibility space as well. So yeah, could talk about this for the rest of the afternoon, but we should probably move on to the next question.
Thanks, Roger. So now there was a question from the chat by Ka Utaresis. There's actually two questions. Let me take one of them first. And that is, assuming the whole world was to industrialize and all people had all the resources they need and thus more light pollution exists in Africa, how would astronomers work around all this light to carry out their observations? And maybe let me start to answer that. Let's see if someone else wants to chip in. Well, I would say it starts with lack of light, not necessarily, or at least for Namibia, not necessarily just talks about lack of industrialization, but also talks about scarceness of population. And quite certainly already now astronomy is done from typically very remote places. And so the further away from big city lights you are, the easier the astronomy is to do. But even if you're closer to inhabited places, like, for example, on the Canary Islands, which are just by sheer size very small, and there's quite a couple of people living there. So they literally have legislation about the outdoor lighting, which is allowed on the whole islands. So, for example, all lights that are outside must be shielded upwards, and you can think that even further. You can think about only allowing light of certain light temperatures. So, for example, only rather reddish light and not bluish light. And well, particularly when it comes to optical astronomy, you could filter that out to some extent. Well, nothing is as good as having pristine skies and having no interference by light pollution there. But yes, there are ways to mitigate. Any addition to that? If not, then I will go to one question that we received on YouTube by Henry Timmer. And that question goes like, because we have heard quite a bit about orientation of spin, particularly of the black hole. And the question is, what determines the orientation axis of the angular momentum of the black hole? And who wants to take that?
I can say for SAG-A, well, let's start. If it's a normal black hole, so suppose one of the ways black hole forms is if you have a star. So this is not true for SAG-A. SAG-A is more complicated. So the first example of how you determine spin is if you have a star that explodes and the star is rotating and it's big enough, then what happens is in the supernova explosion, a whole bunch of mass and ejecta gets shot off. But the star was originally spinning. So then they get shot off. But the spin is retained. Spin is a very conserved quantity. So they lose some of the angular momentum with the stuff that's shot off, but the black hole spin is inherited then from the spin of the star, the original star, if the explosion is not too disruptive. So you can get the spin of that way. So it's the formation of the black hole that influences the spin. Once you have the spin stays there unless something else external acts upon it. Okay. Another thing that determines the spin is if you have two black holes merging, then you get a resultant spin. So you can have two black holes with different spins that merge, and then you'll get a final black hole, and the final spin will depend on the orientation of the first two spins. Okay, so then you can play the game. You can say, let us imagine if the black hole at SAG-A was the result of a whole bunch of bigger or smaller stars or black holes that originally merged together, then its spin could be the result of those, the sum of those spins. The same is true if you have galaxies merging. Its spin could be a result of the black holes and the galaxies merging themselves. So it's the formation of the black hole and the origin of it that influences a spin. My first intuitive thing, if I look at a system, is I think the spin of the system, it will look like Saturn. You have the spin pointing up with a disk around it, any system that has a disk. That is my sort of default assumption. And if I see deviations from that, I start looking at it. Now, the way you do get deviations from that is if you have that object interacting with another one, you can actually pull the spin. So the answer is for SAG-A, I don't know what the formation scenarios are that would cause a spin. And I don't know if it's just that I don't know that it's not known. Another thing is the S stars, as orientations are anomalous. They have always been a puzzle, how they got formed, how they got there in the first place. And part of sorting out the puzzle is actually establishing how that is related to the spin of SAG-A. And that's why I said it's a very, very fertile ground for exploration, what this result now makes possible. One, I'd love to see error bars in the result, which I don't know how certain it is. The second one is, if it is so, then there's explanations to do. And people are working on it, that A. Loeb and stuff are some very good physicists. And it's going to be a fun playground to actually work out how this happened. It's a mystery or it's a puzzle that has to be solved. It doesn't mean that I question the result. It basically means that here's something I don't understand how to explain. It's definitely not what I expected.
Yeah, I would just add one or two additional things to that excellent answer. I mean, firstly, the spin the orientation is highly uncertain with the current imaging quality, and it kind of just underpins why this array needs to be expanded in order to do these exquisite measurements of black hole spin that we're able to kind of now start to slowly tease out. And I think the future is extremely exciting in that regard. It also tells us, in the SAG-A star case, yes, there could have been merger events between smaller black holes, but it also tells us about that accretion disk, that accretion flow that I introduced in the video, and the orientation of sustained accretion episodes and the orientation of that gas can spin up a black hole, and that also tells you about the environment around the black hole. I think another great synergy here is with the SKA and Mercad is the larger scale signposts of these potential black hole mergers, which then change the spin that Jean-Drew mentioned. So a great example of this was the X-shaped galaxy that Mercad imaged with such supreme quality just a couple of years ago. And those sort of large scale signposts of the jets changing orientation are getting at this question of, is this changing spin or is it other external factors? But yeah, I mean, getting down to event horizon scales with the EHT, complementary science with the SK is yeah, it's a very fertile ground, as Jean-Drew mentioned.
Thanks, Roger and Jean-Drew. I see your hands. I just have one question still from the chat, which is quite crucial, I would say, and very important for us to answer here. When I read it, it says it's by Richard Okaya, and it says reproducibility is rather questionable since independent researchers would not be able to check if they do not have the facilities. Reproducibility is the core of science. Before I hand over to our two EHT members here, Roger and Inian, let me, as non-EHT member, give a very first and very short answer to that. And that is, well, firstly, yes, reproducibility is at the core of science, and it unfortunately is in days of mega size experiments not easily given. But researchers are aware of that, so it's not unknown to us, and that is independent of if we talk the SKA, if we talk the EHT, if we talk large size particle experiments like the Large Hadron Collider at CERN. So the crucial point there is that people are aware and that people take measures to ensure reproducibility. My very personal recent favorite in that regard is actually the movie that was done about the first EHT image, which is called The Black Holes, The Edge of All We Know, where very nicely it is showcased what the EHT collaboration, what measures the EHT collaboration took to make sure that their results are in fact robust and reproducible. And with that, I want to give to Roger and Ininyan to share a few more details.
Take away, Inin.
Yeah, I just want to give a short answer, and yeah, Roger can also add to that. So yeah, one of the things that we have been trying to do is to release the data products that would give the calibrated data products that would give rise to the images that we see. And we have this time also, we have taken a lot of pains. I mean, especially a lot of people have worked like day and night to bring out the actual scripts that were used to produce these images from the data with, and we've also been trying to document every software that has been used for imaging and calibration. And I mean, that's just to add to Michael's excellent answer. If this is all modulo that you have the facilities to do it, but then again, the facilities required are not great. A moderately sized laptop can create these images from the EHT data. Yeah, so anyone is free to do that, and the links are available publicly. And Roger, if you have anything to add to this.
No, I mean that's excellent. I would just also add that, you know, some of the world experts in imaging, intermetric analyses have taken that data that as Inian mentioned and was part of in putting a lot of effort into releasing it, and they've done completely independent analyses with those data and came to, you know, the same conclusions, validating and getting results that are completely consistent with us. So that is wonderful to see, multiple independent analyses around the world, but also within the collaboration. I mean, it's over 300 scientists, and what we didn't really have time to cover today, but I think you got a hint of it from some of Indian's excellent slides, with just the redundancy that's gone into this. It's been an extremely careful endeavor and doing multiple techniques trying to tackle the same thing. I think this is important in science, in addition to releasing the data for the public for the broader community, kind of to try and do their own analyses. But yeah, if anyone wants to build a second EHT, that'd be awesome as well.
Thank you.
So I can add something. I'm not in the collaboration, right? And so there's precise reproducibility of the image, but there's also plausibility discussions or a conclusion being drawn, right? Like the measure of the horizon size is the same for the S-stars and for the image. There would have been a problem if it was different, then we wouldn't know whether it is physics or measurement. But because it is the same, the only explanation is that it's the right measurement and there's very little physics in between. The other thing is Marissa or our estimate of the spin of SAG-A was made 7 years ago based on previous data, right? And it agrees entirely with what has come out of the Event Horizon Telescope thing. We made assumptions that we were very clear about. It's a completely different analysis, it's a pen and paper one. And it agrees with what they got. So I believe their magnitude, the thing I drew into question because I don't know how to explain it, was the orientation. But Roger's just said that's not, they don't even claim to have pinned it down strongly because, and that's the only criticism I would get, is they don't state how well they have determined it. That I would make a criticism of the paper. But for the rest, the magnitude of the spin, I think they've got it pretty accurately and it's consistent with all prior results. The mass and the size of the image is spot on. It's consistent with everything else we know. When you do science, you must be very clear of what you know, what is inferred, and what is observed. And you do that and you keep it clear. And currently what the results are, at least the quantitative results I can see are consistent with everything we know. And the technique has the possibility of refining that image and going beyond what we know. And then we will still put in sanity checks, or external people like myself will still come in and ask the questions, does this make any sense? Does this make sense on some other pen and paper calculations that I've made that doesn't resolve on a huge image bank, a bank of images that are made on supercomputers that have a whole bunch of physics in that not individuals might understand. And what is interesting about this pen and paper result that we have is that it makes predictions that I'm going to go and check and see if I can pick up these frequencies, and those frequencies imply certain things for the images that are going to be produced. And then I'm going to see if those actually bear out. So they are independent checks. Not exactly reproducible. I don't have another telescope I can build and use myself, but I do have logic at my disposal.
Yes, thank you. There was quite some appreciation also by the asker of that question, if I may say so. Now we have three hands that I want to give the chance to talk up. There will be Nadim, Uzair, then Jamal, and then Habib Aisayu. And afterwards, there's one more remark from the chat that I bring up as the conclusion. Nadim, please go ahead. Nadim, are you with us still?
Yes, thank you so much, Michael. I have two questions. My first question is, what are the sources of radio frequency interference apart from satellite at this high frequency? And how much do they corrupt the data? And the second part of the question is, how do you correct for tropospheric fluctuations because you have those antennas, okay, across different countries and continents, and the troposphere, okay, they vary. So how do you make that correction to calibrate your data? I don't know if it's too technical.
Well, on the first question, fortunately, electronics is really, and receivers are really, and transmitters are really expensive to build at these high frequencies. So we don't really have any radio frequency interference. So to more public members of the audience, that sound of a cell phone affecting a call, which can corrupt your data or corrupt a telephone call that you're making in yesteryear. We have the analogous thing with radio telescopes, but Nadim, at 230 gigahertz, there are virtually no sources of RFI that we do any kind of flagging of. Now, there might be an issue if you have, side lobes of strong transmitters in the vicinity that are affecting, some of your signal chain. But in the actual data, no, there is no flagging routine apart from looking for bad data where you have sort of more mechanical type data. On the tropospheric corruptions, yes, I mean this is a major issue, right? So at 230 gigahertz, the so-called coherence time, the time that it takes for the atmospheric phase to change the incoming wavefront by about a radian or 60 odd, around 60 degrees, is of order 10 seconds. It can be longer for some of those best sites, the South Pole Telescope and ALMA, but it can be as short as a few seconds. And so what that means is you can't average the data for longer than the coherence time. Otherwise, you're just kind of losing all that information. You're just jumbling it all together and you can't recover it. So you have to sample it below the coherence time. And then on top of that, you obviously, like standard radio interferometry that you are an expert in, with Mercad, you perform your calibration and you make those corrections with the time varying phase.
Thank you, Roger. Jamal?
Yes, hi, Mike. Jamal, yes, indeed. I have back to the comparing the imaging of M87 and the black hole in our galaxy. They basically, as I understand, the same angular diameter, yet it looks like it has been harder to image our black hole. And does the environment of our black hole, since we are looking in the galactic plane, has something to do with the difficulty of imaging our black hole? It took several years later to finalize the data and get this image. And also, now, as I understood, that's the two most simplest black holes that we could image at the resolution we're talking about. But the question was answered somehow before when one of the speakers said that there's a listing of the next targets. But what are is there any galaxy which will have like a supermassive black hole which will be at a reasonable distance? I mean, M87 is at 53 million light years. I mean, do we have real targets, or is just it will be harder, much harder? And what is really realistically the possibilities of imaging all the black holes? And please tell us specific cases of black holes which will be next in line from the two ones we had imaged. Thank you.
I think Ian's well placed to answer the first question, and then maybe I can take the second because it's a follow-up of a previous answer I gave.
Is the first question, why did it take so long to emit?
Yes, why is it harder than M87?
And is it related to the environment of our black hole, since we are looking at it through the galactic plane? So although I know it's in radio, it's not in optical, but maybe is that part of the answer, at least the fact that it was more difficult and it took so much more time?
Yes, that is part of the answer. It's not necessarily the environment at the immediate vicinity of the black hole, but because Sagittarius is bright enough at these wavelengths, but it's what lies between us and the black hole itself. There's a lot of gas and dust through which we have to see this black hole. And that's part of the reason. The other reason is that although Sagittarius star is 1,000 times closer to us than M87 star, it's 1,000 times faster. So like it's 1,000 times smaller, so the material goes around it faster. And that means the structure that you see of Sagittarius star. So in interferometry, one of the basic assumptions we have is that throughout an entire observing night, the structure of the object that you're observing doesn't change much. Only then can you kind of observe it through multiple hours. This doesn't hold true for Sagittarius star because of this rapid rotation of the material around us, and that requires variability mitigation strategies. So all these things had to be developed, and that's why it took much longer than M87 star.
Can I jump in? Because with sort of a partial other question too. So a quick answer is the separation of timescales in M87 is much more favorable for doing imaging than in Sag-A. But my question to you that have actually done this is how much, to me, the stuff you are throwing away or the variability you're throwing away is actually physics. How accurately can you get a periodogram of the changes, say, or how accurately can you resolve the changes on, say, a matter of 4 minutes? Can you have that type of time scale? You don't have to make an image. I just want a Fourier spectrum, and I could say more than I think the images can at the moment.
Yeah, so there's a ton of work on that because, you know, it's a sort of a 4Jansky source. It's really, really bright, and it's rapidly varying. And it's monitored by, you know, there've been tons and tons of monitoring experiments that don't resolve the shadow, but that do trace this, and you know, they published periodograms of this over the years. I think things get interesting when you actually have a spatially resolved periodogram, as you were hinting to. I think there's a whole lot of physics there. At the moment, you know, the algorithms that Ian has worked so hard on to actually enable the imaging and the modeling of this with that variability has kind of been more of a focus, but that gets a lot easier as soon as you add more stations and the physics that you're able to extract. I mean, I think of this as a gravitational laboratory that is in our southern sky, lying right above us, right behind me, that we're able to probe for years and years now in all sorts of ways. And this is one fantastic example that you bring to the fore.
Yeah, I mean, my thing is I don't want you to go away from a Sag-A. That little blurry image must become a refined picture of the structure in the disk. And I think that is possible, but there's going to have to be quite a lot of work on how you separate out what is actually timescale from sort of intervening effects and things that come truly from the core. And that there will need to be some development there. And it's very exciting to see what will come out soon. Well, the one will be experimental and the other one will actually be ways of looking at the data.
I think the bottom line there is, and put in very simple words, we'll try to add more stations to just not just make an image, but literally a movie. And then we have literally what Roger meant by spatially resolved periodograms. With that, we had actually one hand going down, another one coming up. So let us have Dlamini last question, and then, as I mentioned, there's one more rather comment from the chat.
Hello. I'm afraid I can't start my video, but may I make a general comment, please? 60 years ago, I did my postdoc on nuclear astrophysics at Caltech. At that time, I went the nuclear route and not the astrophysics route. John Drew, well done. I wish I'd done astrophysics. Then, to look at 60 years ago, I lectured actually nuclear generation in the stars to Bernie Vanneroff. And I paid tribute to the way he started the SKA and really carried that forward. Today, I look at Michael, Roger, Inyan, and I say, what a bright future we have in Africa for astronomy. I'm thoroughly impressed by the Global Young Academy, and to you, I will give you my fullest support and every best wish for success in the future. And may you get into the millimeter band soon, soon, soon. All the best. Thank you, Don.
Thank you, Don.
Thank you so much, Don.
Thank you very much.
Well, this would be an excellent note to close on, but as I have promised already, there's also another very great note from the chat I want to close on. And bear with me, it's a little long a read, but I think it's quite worth it, and then we might have very short concluding comments around the podium. And this comes from Ka Uta Tresis. By the way, sorry if I pronounce names wrongly. That's certainly not my intention. The comment, I read it here. Xavier Barson, the Director General of the European Southern Observatory, who said in the press conference to announce the findings that, quote, "This extraordinary result would not have been possible to achieve by one single facility or even the national astronomical community of a single country. It took 8 radio telescopes around the world, and that network has already expanded to 11 today. Many built, funded, operated, and supported through international organizations across many countries around the world." He then further continues with, sorry, I'm scrolling through the chat. Bacon says, again, quote, that this discovery shows what we can achieve when we cooperate, when we work together. This is very important to remember in the times that we are living in, where the world is not running in that direction, unfortunately. And the question by the, or the comment by the poster was, could the speakers here comment on this statement and how this achievement provides us with a glimpse of what humanity might achieve if we were to base ourselves and goals on science, or not on conflict and greed.
Black heads and this and that and that. And it then got into the young.
And yes, I want to give a moment to let that sink in, and then maybe I start commenting on that. And well, I very personally am a strong believer in also international collaborations. And well, as you've noted, I'm part of the HES collaboration, which well brings together people from from 14 countries around the world. And I also mentioned the Global Young Academy earlier, which is not quite a scientific collaboration, in a sense a similar setup, where we have members from more than 80 countries around the world, amongst the 200 members that we are strong. And yes, I personally feel that this literally is the way to go, and that well, any journey, whichever pathway it takes in science, or actually even not just in science, but let me stick to that example here. If you can make use of the strength of the different people, the group achievement will be so much stronger. That's what I personally quite strongly believe in. And with that, I want to give it to the other panel members.
Well, I would just comment on how it's just such a privilege to be able to do science like this in what are globally challenging times, and to do so with large international teams from diverse backgrounds and cultures is just incredible. And it's just a way of kind of, there's just so much more that unites us than than divides us. And I think, you know, Jean-Louis was excellent in kind of just bringing us back to the shared wonder of this black hole at the center of our galaxy. You know, that we're, you know, this is the EHT collaboration, but for all of humanity to kind of the shared wonder of this. And that's just one example of these what these major scientific international collaborations can do. And I think for Africa as a binding agent, I think very long baseline interferometry is one such route to fostering this and building this. And I really look forward to that over the next decade at multiple frequencies. But yeah, just what a privilege to be able to do science in what are very, very challenging times.
Jandro, Inyan, any final words on that?
Science has always been a competition between collaboration and competition. In some sense, the competition to distill the truth and collaboration the effort. And if you set up an environment in which both are possible and both thrive, and you will clarify the truth to a greater extent than any individual can do. And it's wonderful to be part of something like that and to learn from each other and in some sense celebrate what the human mind can do and what we can build and what we can see and what can be understood. I mean, what this particular result does is it looks further into the Galactic Centre than we ever have. With it comes questions, with it comes a beating down of dragons, and with it comes a bit of imagination of what could be there, what have we missed? I mean, our understanding of the universe is not complete, and there's a humility necessary to accept that, and there's a joy in going after and clarifying what we know.
Thanks, Jandro.
Yeah, well, I don't really have much to add to those excellent answers. It's just, yeah, you know, we keep trying together as a species, and yeah, sometimes we may stumble, but yeah, we keep forging ahead. I can only hope that international collaboration in science will continue to grow in through projects such as the EHT and with the African expansion. And yeah, I think these are good times to look forward to. So yeah, I'm hopeful.
Thank you, Injan. With that, we come to the very last point that I have on the agenda, and that is essentially concluding remarks. But before I hand over to Charles for that, I want to wholeheartedly again thank the DSI and AfAS to have us all here today, to give us the opportunity to try to make a bit of more sense to the wider public as well of these great results that were recently published. And I want to thank, in addition, also Charles and Niju and all the team who literally worked on all the technical side to keep all this running. This is very much appreciated. And with that, I wonder if Charles Takalani has some concluding words for us.
Thanks. So firstly, I'd just like to thank everyone that joined the session. I don't think it would have been a success without everyone that participated today. And I'd like to thank you, of course, Michael, for chairing this session very well. I think you did a great job. I'd also like to thank all our speakers, Roger, Inyan, Jandro, and also some of the great comments that we received from Don Menge. The future is indeed bright for astronomy in Africa, and it's up to us to continue shining that light and to take it into the future. And of course, I'd like to thank the DSI for the support that they've given AfAS, and that and in making all of this possible, in helping us grow astronomy on the African continent. And I set you all free now. So enjoy the rest of your afternoon and have a great weekend. Thank you.
Thank you, everyone.
Yes, thanks everyone. With that, all the official proceedings are closed. Thank you and see you next time.